Unfortunately, I've once again had problems recording the lecture, so I've had to re-record this one. So that's why the audio sounds different once again. Okay, so things to note this week. Exercise 4 is up. There are no truth tables in this exercise, which is something that we're going to learn about today. I'm going to post truth table practice on Quarkus. There are some symbolizations in this exercise, which are somewhat harder than the ones you've seen before, but involve all the same basic skills. There are also derived rules, derivations where it makes sense to use the derived rules. Of course, with derived rules, it's never strictly necessary to use them, but they are very handy in solving these. The other thing I'd like to note is that just doing these exercises is not enough practice. It is not enough practice to just do these in order to do very well on the test. If you're hoping to do very well on the test, you're going to want to do a lot more practice. You currently have all the skills that you need to do all of the derivations from chapters 1 and 2 and all of the symbolizations from chapter 1 and 2. So if you want more practice, there's loads available to you. And I would just like to remind you that I strongly recommend that you practice pencil and paper. Practice pencil and paper and then input what you've got into Logic 2010 to check whether it's right or not. Because on the test, you're not going to have Logic 2010 filling in the details for you. So Logic 2010 provides the outputs to rules, which is about half of the work of doing a derivation. It also provides you quick checking to see whether you've done something right. So all of that is helpful scaffolding to get you to learn the basic skills, but on the test, you're going to need to do all of that yourself. So if you're only practicing on Logic 2010, you're only doing about half of the practice. For derivations especially, I've put the blank derivation sheets on Quarkus. I strongly recommend that you print out some of those and do your practice on those sheets, because those sheets are exactly what you'll see on the test. So you'll be practicing exactly the skills that you need to succeed on the test. Okay. Speaking of the test, it will be in the regular classroom during regular class time on February 11th. So we'll start right at 3:10 and it'll run until 5 p.m. The content of the test is as follows. There'll be one full truth table and two shortened truth tables. It'll be clear what that means by the end of this lecture. There'll be one short answer question about some of the central concepts that we've talked about in the course. There'll be 6 symbolization questions, which will be fairly difficult. They won't be simple, straightforward ones. They will be fairly complex. So we'll do a little bit more practice on Wednesday at the level that the test will be. Furthermore, there'll be 2 basic rules derivations, which is rule derivations where you're only allowed to use the basic rules. That is, you're not allowed to use the derived rules that we introduced last week. And there'll be 2 derivations where you are allowed to use the derived rules. So time is going to be a factor. You do want to practice getting quick at these things. Most people find that about half of the class last semester was able to finish before the end of the test, but that's because they practiced getting quick. So on to this week's material, which is truth tables. So truth tables are another diagnostic tool that we have in our sort of toolkit. You can do a whole bunch of different things with truth tables. For example, you can apply them to just sentences or sets of sentences. You can tell about a sentence whether it is a tautology or a contradiction or contingent. And I'll explain what those things mean in just a minute. And you can also tell of a set of sentences, a collection of sentences, whether they are consistent or inconsistent. And we can also apply truth tables to arguments. So we can use truth tables as a test to see whether an argument is valid or invalid. Now we've already got an important tool for testing whether an argument is valid, which is our derivations. Derivations show you that if you've completed a derivation, that is, if you derived the conclusion from the premises, then you've shown that the argument is valid. Up to now, however, we haven't had a good tool to prove conclusively that an argument is invalid. If you're unable to complete a derivation, that's some evidence that it might be invalid, but it's certainly not a proof. It could be just that you can't see how to complete the derivation. So a truth table is a really nice way of proving conclusively that an argument is invalid. And of course, you can also use it to prove that an argument is valid. So just recall very quickly the fact that our connectives are truth functional. So these are the truth tables that I've been showing you all along for our connectives. And in some sense, these are definitions of connectives. That is, they tell us how these connectives behave in an input-output kind of way. Each connective takes the atomics or the simple sentences that it binds as inputs and outputs a truth value. So if P is true and Q is true, the connective and outputs the truth value true. So this is true of all of our connectives, and these are the basic building blocks that we're going to use to build our truth tables about larger sentences. So the basic outline of a truth table is as such. We're going to start with what are called truth value assignments. That is, we're going to start with a table of all of the possible assignments of truth values to the atomics. So suppose we've got a sentence that's just got P and Q as atomics. We're going to start with all of the possible ways of assigning true and false to P and Q. They could be both true, they could be both false, one false, the other true, and so on. So we just start by listing all of the truth value assignments that are possible for those atomics. And when we're building a truth table, we start by just distributing the truth values of the atomics across all instances. And then you work your way up from the smallest parts towards the major connective. Let me show you what I mean by that. So this is a thing that we're going to build a truth table for. This is just a sentence. If P then Q, and if P then not Q, then not P. So let me show you the procedure for taking these truth value assignments. So on the far left, we've got just the truth value assignments for P and Q, and then we're going to apply those to all of the instances of P and Q, and then figure out what the truth value of the connectives are. So do this by hand, because you'll be doing it by hand on the test. So this is just the same sentence. If P then Q, and if P then not Q, then not P. So the first step, so I will, on the test, I will give you something that looks quite a bit like this. That is, I'll give you the atomics, and then the sentence or the argument, and then I'll generate for you the list of all the possible truth value assignments. So this will be, you'll start with this. Now, your task is to first just copy the column under P for any instance of P. So we're just copying basically what we see on the far left under all of the instances of the atomics. True, false, false. And then copy the Q under every instance of Q. True, false, true, false. True, false, true, false. Okay, so that was distributing the truth value assignments of the atomics across the sentence. Now we're going to work our way up from the smallest parts of the sentence towards the major connective. So this involves your parsing skills, where you're trying to figure out what the smallest parts are, and then the medium parts, and then the biggest parts. So in this sentence, we've got two connectives that could be potentially the main connective, the and the conditional. Of course, we have blatant favoritism towards conditionals, so this is our major connective. Okay, so we're just going to build up, and these are our smalls. The brackets indicate that this is a small part and that this is a small part. And of course, recall that the negation signs always attach to the smallest part that they are adjacent to, that they're just beside. So let's do this conditional first. Now this requires that you remember and have internalized the truth table for the conditional, because we're going to take P as input for the antecedent, Q as input for the consequent, and then you have to remember what that makes the truth value of the conditional. So if P is true and Q is true, that makes this conditional true. if P is true, the antecedent is true, and the consequent is false, that makes the conditional false. And anytime the antecedent of a conditional is true, like in these two cases, the whole thing comes out as true. Okay, so this requires, basically I've just written out again the truth table for the conditional. That is, I've remembered what the output of the conditional is given these inputs. Okay, so now a slightly more complex case where what we have to do is use P as the antecedent, but not Q is the consequent. So we can't just take the truth values of Q, we have to take the truth values of not Q as inputs. So to figure out what the truth value of not Q is, we of course just flip the truth value of Q. So anytime Q is true, this comes out as false. Anytime it's false, this comes out as true. Okay, so now we've got the input for the antecedent of this conditional, that is the P column, and the consequent, that is the not column. Okay, and now we just do the same thing that we did before, just remembering what the truth value of a conditional is given these inputs. So if the antecedent is true and the consequent is false, that makes the conditional false. True and true is true, and anytime the antecedent is false, it is true. Okay, so we're just gradually building up to from the smallest parts to the biggest parts. We can figure out the truth value of this conditional, or this conjunction now. We're going to use as input the truth value of this conditional, because that determines the truth value of this whole part of it, right? So the truth value of this whole part of the sentence is determined by the truth value of the conditional. So that's the input for the one part of this conjunction, and this determines the truth value of this whole thing. So that determines the other part. And recall the truth table for the conjunction says it's true only in case both halves are true. So I'm just going to look at this column, and anytime they both say true, I'll write true here, and anytime they don't, I'll say false. So this one's false, so it comes out as false. True and false comes out as false. True and true comes out as true. And true comes out as true. Okay, let's do this. Not P, this just flips it. True, true. Okay, and now we're in a position to assess the major connective, the main connective of the sentence. So we're going to take as inputs to this conditional the value of this conjunction, right? And then the value of this negation, because this whole thing is the antecedent of the conditional, and this thing is the consequent. So the truth value of this whole sentence is determined by the truth value that we assign to this conjunction, so that's this column, and the truth value of the consequent is determined by this whole sentence, which is determined by the truth value of the negation. Okay, so using the truth table for the conditional, if the antecedent is false, it's true. Antecedent is false, it's true. The antecedent is true and the consequent is true, then it's true. And if the antecedent is true, the consequent is true, then it's true. Okay, so now we've successfully built a truth table for this sentence. And the most important column in this truth table is the column for the major connective, this one. That tells us, given all of these truth value assignments, how the truth value of the whole sentence comes out. Now this particular sentence has got an interesting property that it comes out as true on every line. So for any assignment of truth values to P and Q, the whole sentence comes out as true, which makes this sentence a tautology. So let's talk about tautologies very briefly. Okay, so a tautology is a sentence that comes out as true on all truth value assignments. That is, another way to say that is, if the major connective comes out as true for all rows, then the formula is a tautology. Tautologies are sort of philosophically interesting. because they're always true. And the fact that they're always true kind of tells you that they don't tell you much about the world. So a tautology is true regardless of how the world is. It's true in all logically possible cases. So it's nice, it's true. It's not that it doesn't tell you anything. It is certainly true, but it doesn't tell you anything about the world. Okay. So that was this that we just did. Now we can test for something whether something is a tautology by doing these truth tables. So our next question is this sentence a tautology? And we'll do this test. So the same procedure as before. I'm just going to copy the values of these truth value assignments under the atomics. So every time I see P, I'll just copy the P column that I see here. Anytime I see Q, I'll copy the Q column. True, false. Okay, and then I'll just do the same procedure that I did last time, which is to build up from the smallest parts to the largest parts. So this negation attaches to the smallest sentence that it's adjacent to. The smallest sentence is adjacent to is this Q. So it just, the value of the negation is just the flip side of the value of Q. And the same for this negation. False, true, true. Okay. Now we evaluate this conditional first because it's a smaller, it applies to a smaller part of the sentence than this conditional. This conditional is our main connective, so we have to evaluate that last. Okay. So this conditional takes as inputs the P column and the stuff under the negation column because this is the antecedent and this whole thing is the consequent. So if it's true and false, then it's false. True and true is true. And any time that it's false, has a false antecedent, it comes out as true. Okay, and now we can use this column as input for the antecedent and this column as input for the consequent, because the antecedent of this conditional is this whole sentence and the consequent is this whole sentence. So we need to figure out what the truth value of this whole sentence is, which is determined by its main connective, and what the truth value of this whole sentence is, which is determined by its main connective. And you take those as inputs to this conditional. So antecedent of a conditional is false, it comes out as true. If the antecedent is true and the consequent is false, it comes out as false. True, true is true, and true, true is true. Okay, so once again, this is the most important column in the truth table because this tells us, given these truth value assignments, how does the whole sentence come out? Now, this whole sentence is not a tautology. It's not a tautology because this F here, that is, something is a tautology if it comes out as true on every single line. But this sentence could actually be false. Given P being true and Q being false, this whole sentence comes out as false. So this is not a tautology. It is contingent. Right. So we've seen tautologies, we've seen contingent sentences. Let's also talk about contradictions. So a contradiction is a sentence that comes out as false on all truth value assignments. So if the major connective comes out as F for all rows, then it's a contradiction. So here's something that ought to work out as a contradiction. We'll do that again. Okay. And one more time. Just start by copying out the truth value assignments on the far left. True, false, true, false. And we work up from the smallest parts to the largest parts. You might be tempted to think that this negation applies to this P, but recall that negations apply to the smallest thing that they are adjacent to And this whole sentence is the smallest thing that this is adjacent to, because the brackets tell us that this is a unit. So we need to first work out this column for the or, and then apply the negation to that. So recalling the truth table for the disjunction for or, it's true anytime either of its disjuncts are true. So true and true gives us true, true and false gives us true, false and true gives us true, and an or statement is false only in case both sides are false. Okay. Now we can do this negation. So the negation flips the truth value of this whole sentence, and that truth value of the whole sentence is given by this. So we're just going to take this column and flip it. False, 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 true. Okay. So this conjunction takes as its inputs this negation column and the P column. And we're going to recall the truth table for the conjunction. It's true only in case both sides are true. So false and true gives us false, false and true gives us false, false and false gives us true, and false and true and false gives us false. Okay, so what we've shown then is that given any way of assigning truth values to P and Q, this whole sentence comes out as false every single time. That means that this sentence is a contradiction. Okay. And a contingent statement is just one that's neither a contradiction nor a tautology. We saw that in the second example, where some of the rows came out as true, some of them came out as false. So you can't tell that that sentence is true or false just by the logic of the sentence. What we need to know is what's the actual truth value assignments. So we're looking at a truth table looks at all of the possible truth value assignments. And if it's a tautology or a contradiction, you don't need to know what's actually true in order to figure out the truth value of the sentence. With a contingent sentence, one where there are some true and some false rows, you do need to know what the actual values of those sentences are to figure out whether the sentence is actually true or false. And one final thing that we can do with these truth tables is show that a set of sentences is consistent. So a set of sentences is consistent if they can be true all at the same time. That is, we just build a truth table with all of the sentences in it, and if there's any row in which they all come out as true, then they can all be true. Otherwise, they're contradictory. So if there's no row where they all come out as true, then those sentences contradict each other. So here are just two sentences, and I'm just going to do this one, I hope you don't mind, in PowerPoint. So just to speed things up a little. I'll just copy and paste these. Something to note here, since we've got 3 variables, we've got 3 atomics, this list is much longer now. So we need 8 rows instead of 4. With 2 variables, we needed 4. With 3, we need 8. The number goes up and up exponentially. So you'll need 2 to the n rows, where n is the number of atomics in the sentence. So you can see that this is only going to be a useful technique for relatively small sets of sentences. Nonetheless, it is useful in some cases. So let's assess the truth value of the smallest parts of this thing, just as we were doing before. So the smallest parts of this first sentence start with the not P. So it's just flipping the truth values of P, and now we can assess the truth value of the conditional. So taking the not column, taking this column as one input and R as the other. So false and true is false. Anytime the antecedent is false, it comes out as true. True and true is true, true and false is false, true and true is true, true and false is false. Okay, that's it for that sentence. Now let's do the other. We'll just flip the truth value assignments for Q to get the truth value of not Q. Do the same thing for R, just writing in the opposite of the truth value. Okay, now we're going to take this column as input for the antecedent. The truth value of not Q is the antecedent, and the truth value of not R, which is in this column, as the consequent. Okay, so antecedent false, it comes out as true. True and false is false. True and true is true. Oh, those should both be true because the antecedent is false. True and false is false, and true is true. Okay, so now we've completed the truth table for these set of sentences. We've seen how various ways of assigning truth values to the atomics, those are these rows, result in truth value assignments for the major connective of these sentences. Just highlight this for you. So what we're going to look at in order to assess whether these sentences are consistent is the question, are there any rows in which both of these come out as true? And if there's even one, then those sentences are consistent. And indeed there are. So the first two rows here, these two set of truth value assignments show us that this sentence is consistent, or these sets of sentences are consistent. There's a couple more down here. So lots of ways in which these two sentences can both be true at the same time. Okay, so that was assessing consistency. So what I've just showed you is that you can use these truth tables to tell a few things about sentences or sets of sentences, whether they're tautologies, contradictions, or contingent for individual sentences, and for sets of sentences, whether they are consistent. Okay. Another really important thing that we can do with truth tables is to determine the validity of arguments. So determining the validity of arguments is very similar to what we just did, except instead of just a set of sentences, now we've got a set of premises and a conclusion. So we're going to just use those exact same skills that we've been building up to build a truth table for an argument. And then once we've built our truth table, we can use it to diagnose a few things about the argument. For example, if there's a row where the major connectives of the premises are all true, but the conclusion is false, it's an invalid argument. Remember our definition of validity. So an argument is valid just in case there's no possible scenario in which the premises are true, but the conclusion is false. Well, now we have, using these truth tables, a very clear way of explaining what we mean by possible. In this case, we are looking at all the possible assignments of truth values to the atomics. So if there is any possible truth value assignment to the atomics in which the premises all come out as true and the conclusion comes out as false, then the argument is invalid. And if there is no such row, if there is no row on which premises are true and the conclusion is valid, then the argument is, or the conclusion is true, false. If there is no row on which the premises all come out as true and the conclusion comes out as false, then the argument is valid. So I actually made an error the first time I recorded this, so I'm going to do it again and hopefully do it right this time. Okay, so I'm just going to grab our truth values for the atomics and distribute them. Okay. And just like we did with the previous problem of doing consistency among sentences, we're just going to do one sentence at a time, building up from its smallest parts. So taking P as the antecedent and Q as the consequent, this is true, true, false, false, and true in any case where P is false. Now we can take a look at the and, which is a function from this column, this conditional column, and r. So if they're both true, then it's true, and in any other case, it is false. True, false, false, false. Okay. And now we are going to deal with the second sentence. So this negation attaches to the r, so it's just a flip side of whatever that says. True, false, true, false, true. And now we can finally do the last column, which is or, so it's not r or p. So if either not r or p is true, then it's true. So true, 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 false, true, true, true. Okay. Okay, so now having built this truth table, we can use it to diagnose whether this argument is valid or invalid. So what we're going to do is start from just those lines on which the conclusion is false, because those are the only ones that are interesting to us in this sense. They're the only ones that could end up showing that the premises are all true and the conclusion is false. So I'll just highlight these to bring them out. Okay, now our question is there any row or any column on which all of the premises are true and the conclusion's false? Just highlight those. Okay, so on this line, the first premise is false. So no good. The first premise is false on this line as well. So that's not very interesting. This premise is false, and this premise is false. So on all four of the lines where the major connective of this premise or of the conclusion is false, there's 4 lines in which the conclusion comes out as false. On all 4 of those lines, at least one of the premises turns out to be false. So there is no line on which all the premises are true and the conclusion is false, meaning that this argument is valid. That's the very definition of validity, that there's no possibility, that is, there's no possible assignment of truth values to the atomics in which the premises are all true and the conclusion false. Okay, let's do another example. So, once again, just distribute the truth values of the atomics to the rest of to each of the columns where they appear. And then build up from the smallest parts of each sentence to the whole sentence. So, not. Good. And then taking the not column and the r column as our inputs, we've got true, 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 because anytime the antecedent is false, the consequent is true. True, false, true, false. Okay. Moving on to the next sentence, the if not Q, then not R. We've got false, false, true, true, false, false, true, true, because we're just flipping the truth values of Q. And the same thing for this. Okay, and now we can evaluate this conditional using the inputs from this not column and this not column. Okay, so true, true, that is false, true, 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 false, true. Okay, so now we're going to do the exact same procedure as we just did last time. So we're going to focus in on just those columns where the conclusion is false, and then looking at those columns, we ask ourselves, are there any column or any, sorry, focus on the rows where the conclusion is false, and then we ask ourselves, is there any row in which the both premises, the major connective of both premises, are true and the conclusion is false? Once again, we can see that there is. So this is the row. So on this row right here, we've got the major connective of this premise coming out as true, the major connective of this premise coming out as true, and the conclusion coming out as false. So that's assessing the validity of an argument using full truth tables. Okay. So, now I hope it's fairly clear that this is a useful technique, but I also hope it's clear that this can potentially get very cumbersome very quickly. These truth tables are super useful for assessing arguments with not that many atomics and arguments with not that many parts to them, because the more atomics you have, the more rows you need, the more parts the argument has, the more columns you need. These things can get really enormous really quick. So it would be nice to have a shortened version of this. And in fact, that's what we're going to show you now. So shortened truth tables. So shortened truth tables have slightly less functionality than full truth tables. That is, you can't prove using a shortened truth table that an argument is valid. What you can do, however, is prove that it's invalid. So I'm going to show you this method now of kind of in a fairly quick and straightforward way, relative at least to the full truth tables, prove that an argument is invalid. So let's look at some examples. Okay. So here we are with this argument, and we would like to know whether this argument is valid or invalid. Suppose we have a suspicion that it's invalid. So we're going to go about trying to prove that. Step one is just to list off all of the atomics in the sentence. This one has 3 atomics, so we'll create a little chart for all of the atomics. Okay, and then the goal here, if we're going to try to prove that this thing is invalid, the goal is going to be to find a way of assigning truth values to these atomics such that the major connectives of the premises come out as true and the major connective of the conclusion comes out as false. So if we can find a truth value assignment that does that, then we've proven that the argument is invalid. Okay, so this takes a bit of sort of searching for what we know, what we can infer, but the fact that we start with true and false gives us a nice starting point. So let's look at the conclusion first. We get a lot of information here. We know that this disjunction has to come out as false. There's only one case in which a disjunction is false, and that's where both sides of it are false. So we know that P is going to have to come out as false. We can write that down here. We also know that not R is going to come out as false. I'm going to write false above the connectives and below the atomics, if that's okay. So we know both of these sides of it have to be false. That means that P has to be false. Not R has to be false as well. If not R is false, that means that R must be true. We can write that down here as well. Okay, so we're most of the way done already. Just having looked at the conclusion, we have at least 2 of the truth value assignments that need to be the case if we're going to prove that this thing is invalid. Now it's just a matter of figuring out what Q should be and then checking to make sure that these 2 still come out as true. So anytime you assign a truth value to an atomic, it has to be the same in all instances. It's got to be the same truth value every time it appears in the argument. So we can copy that out, and we can copy out the truth value for R. Okay, so looking at this first premise, if we know that P is true, we know that not P, if we know that P is false, we know that not P must be true. And if you recall the truth table for the biconditional, it says the biconditional is true just in case both halves are either both true or both false. The biconditional says these 2 things have the same truth value. So if not P is true, that means that Q has to be true as well. So I'll write that down here. So this is our answer. This is it. What we've come up with here is a truth value assignment on which the premises are true and the conclusion is false. I just want to check, so before I proceed, before I call it a day, I've checked this one and I've checked the conclusion. Let me just check to make sure this comes out as okay. So I said that Q is going to be true, P is going to be false. So if P is false and Q is true, this disjunction comes out as true. Now, if this conditional has a true antecedent and a true consequent, then it comes out as true. So hooray. That is, we've confirmed, made sure that we did in fact get a truth value assignment. P is false, Q is true, R is true, on which both premises are true and the conclusion is false. So this is a proof that the argument is invalid. Okay, let's do another example. Right, so once again, the procedure is as follows. We just start with a list, Q, S, V, X, of all of the atomics in our argument. And we start with the assumption that all of the premises are true, and the conclusion is false. Okay, so given that the conclusion is just an atomic here, we already know that Q has to be false. We can write that out. Anywhere Q appears, we can place that in there. Okay, what else have we got? We know that not X must be true. That's one of our premises, so this whole thing has to come out as true. And if not X is true, that means that X must be false. Write that down there, and we can distribute it here. Okay. Now what? Well, we've got a clue here as well. So we know that this conditional is going to have to come out as true, but we know that the consequent is false. And that tells us that, so the only situation in which the conditional is true but the consequent is false is if the antecedent is also false. So if this had been a true antecedent and a false consequent, then this conditional would come out as false. And we can't have that, so we know it has to be false as well. So good, now we know that V has got to be false. And once again, distribute it here. If we know that V is false, we know that not V has to be true. That's helpful, because now if we know that the antecedent of this conditional is true, and it has to be because not V is false, so not V must be true. If the antecedent is true and the whole thing is true, that means that the consequent must be true as well. So now we have our truth value assignment for S. And so this is our answer. This is the thing that we're looking for. And I'm just going to really quickly check to make sure I didn't cause problems for myself here. So if S is true, then not S has to be false. But that's okay because the antecedent is false. So this conditional is going to come out as true one way or the other. Okay, so once again, I've come up with a truth value assignment on which all of the premises are true and the conclusion is false. Okay, one more. Okay, so this is a big complicated one. So once again, same procedure. R, Q, S, T, W. Okay. Good. And we're going to assign true to the major connective of all of these premises and false to the conclusion. Okay, so it's kind of nice to have a false conclusion in here, especially a false conditional, because we know that there's only one circumstance in which the conditional comes out as false. Conditional is only false when the antecedent is true and the consequent is false. So if we know that this consequent is false and is not W, then we know that W must be true. Good. Okay, and then we can write that value anywhere we see W. Well, actually, we must write that value anywhere we see W. We can't yet tell for certain whether Q or S is going to be true. We know that at least one of them must be true because we need for this whole sentence to come out as true in order for this conditional to come out as false. But it's not yet obvious which one or both should be true. Okay, so what else can we tell? We can tell, for example, with this premise, a true antecedent and a true conditional. That means that this has to also be true, because if this was a true antecedent and a false consequent, it would come out as false. But again, it's not super clear whether R or P is doing the work of making this thing true. So let's just leave that for now and look at this premise where we've got a true negated biconditional. Okay, so true negated biconditional means that the biconditional must be false. And once again, we can tell that if it's a false biconditional, it just tells us that S and T have different truth values. Okay, so in some sense, we are a little bit stuck here because we haven't got any conclusive evidence about R, Q, S, or T. So you'll sometimes find yourself in a position like this where you really just have to try something and see how it works. You try something, see what consequences it has, and then if it works, then great. And if it doesn't, then you try the opposite thing. So there might be some guessing and checking involved here. And that looks like the position that we're in now. We kind of have to start guessing and checking. So let's start somewhere. Let's just say that R will make it true. This is just a guess. I don't have any evidence that that's the case, but if I'll try that, see if everything else works out, and if it works out, then we're done. Okay, so what consequences would it have if R is true? Well, this biconditional has got to be true, meaning this thing has got to be true as well, meaning Q has got to be false. Let's try that. Okay, so if Q is false, it appears here as well. Well, that means that one of these has got to be true for the disjunction to be true. So that means that S has to be true. Okay, so if S is true, then we can tell something about this, because this biconditional being false implies that these two have to have different truth values, so T has to be false. Okay, so R is true. Oh, and I forgot, as I did in lecture, I forgot one more of our variables here. I forgot to write anything for P. P only appears here once. It's not super important to working out all of the... P appears only once in this argument, and it appears as part of a disjunction. We already know that part of it is true. So it really doesn't matter what truth value is assigned to P. Nonetheless, let's assign one. Let's call it true. Why did I pick true there? It could have been true or false. Doesn't really matter. I'm going to pick one or the other just so that I've got a complete truth table. Okay, so good. What we did there was really just guess. We just said, let's try assigning true to R and see what happens. And that had a whole bunch of consequences for how we evaluated the rest of the truth values. But as it turns out, we guessed in a way that did generate a truth value assignment, this whole thing, on which the premises are all true and the conclusion comes out as false. So we've successfully proven that this argument is invalid. Okay, one last example and that'll be it. Okay, so P, S, T, Q, R, and W. P, S, T, Q, R, T, W, R, S, W, W, Q, T. Okay. This is me attempting to learn from my previous mistake, not leaving out any of our atomics. Right. Okay. So, once again, we start from the assumption that all of the premises are true, identifying, of course, their major connectives, and that the conclusion is false. Okay. Once again, we've got a false consequent as our conclusion, which is kind of nice because we know that the antecedent must be true and the consequent must be false. So we've got a hint already. We know W must be true. We can fill that in here and here. We don't yet know whether Q and T are Q is true and T is false, or the other way around. So let's just leave that for now and hope that it gets cleared up later. Okay, so let's look at this. We've got W being true, which means that not W must be false. But this disjunction we've assumed is true, meaning if one disjunct is false, it must be the case, this is the rule modus tollendo ponens, that the other side is true. So in order to make this disjunct true with one half being false, S must be true. We can fill that in for any other instances of S. Okay, now what have we got? Let's see. So, okay, so here we've got some more information. We know that S must be true, which means that regardless of the truth value, if one side of the disjunction is true, that means regardless of whether P turns out to be true or not, we know that this disjunct has to be true. This disjunction has to be true. And if one half of this biconditional is true, and the whole thing is true, that's got to be the case that this is true. So good. We know that T must be true. Okay, so we can fill in T for here. We know now that this has to be false. So if T is true, not T has to be false. So that doesn't help us much in determining the truth value for R, unfortunately, because it's just unclear whether given that it's got a false antecedent, this could be true or false. But we've got some information here, right? So I can fill in T because we know that T has got to be true elsewhere in the argument. We know T is true, but we know that this biconditional is false, which means that in order to make this biconditional false, these have to have different truth values. So Q has to be false. Good. We can go through and fill in Q everywhere. And now, given that this biconditional is true and Q is false, we know the biconditional says these two things have the same truth value. So if Q is false, that means that R has to be false as well. Fill in that. Good. Now, once again, P only appears once in this whole argument. That's okay. It really doesn't matter. Once again, P, it doesn't matter whether we assign true or false to P. Either way, this disjunct comes out as true, and so this comes out as true. All right. So once again, what we've done is come up with a truth value assignment on which this argument is invalid. That is, the major connectives of all of the premises are true, and the conclusion is false. Just a couple notes on doing these things. All of this stuff that I've written up here is not actually part of my answer. The stuff in the box is the answer. So that's what you'll be marked on coming up with like a truth value assignment is the actual job here. Another thing, I wrote T or F here. I kind of recommend that you just pick one because it's less committal. If it's true that it could be either T or F, then you get full marks for writing T, or you get full marks for writing F. If it turned out that it did matter, then you don't get full marks for writing T or F. You just write T or F. So it's less, it's just a little bit less risky to just pick one and write it in. If you think it could be either, just pick one and write it in. One more thing to note, students are often tempted to draw for these and the full truth tables something like this, which is neither a T nor an F. So if you write that, then you get no marks. This is not an interpretable sign in our system. You need to have it be either a T or an F. Yeah. Okay. So that is shortened truth tables. So that's it for this time. Next time, we're going to just do test review. So we'll do a bunch more examples. We'll do some more difficult symbolizations, do some derivations.